4, it's like you're learning a whole new technique. So drink your coffee before class next time. 6.3. We have multiplication of polynomials. Basically, we just use the stuff we learned in our first section. We just kind of put pieces together a little. So, for example, I'm going to use a problem straight from the text because I think that's still appropriate. We'll look at this through examples because that's kind of all it is. We have 3x squared times a huge polynomial. It'll have 3 pieces. It'll be called a trinomial. We'll have 2x squared minus 5x plus 3. So the idea with this multiplication of polynomials is, hey, we've got pieces times pieces. What are we going to do? Well, hopefully not freak out. Remember, the first thing you do is look in parentheses. Do you have any like terms in those parentheses that you can put together? No, that's what you practiced last time, isn't it? Adding and subtracting them. That thing's already condensed. But we have parentheses that we like to break down. To break them down, we do something called what? Distribution. Okay, good. I wanted to make sure I was actually recording. Okay, so we take this one, the piece out front is attached by multiply, and we distribute or share it to every piece on the inside. So when I multiply the first piece, I have negative 3x squared times 2x squared. Okay? Negative 3 times 2, what do I get? Okay, negative 6. X squared times x squared, what do I get? You got it, because I add those powers, right? So that's something you got to remember. Okay? Now then when I look at that to negative 5, I say negative 3 times negative 5, I'm going to get what? What kind of 15? Positive 15, okay. X squared times a plain x gives me x to the 1 plus 2 is 3, okay. Because remember there's that power of 1 if I don't, there's a power of 1 on that x that I'm not seeing always. Okay, negative 3x squared times a positive 3. You got it. Negative 9, and we don't have any x's to add powers on, so we just keep what we have. Can I combine anything now? Adding and subtracting. Not in the like terms. No like terms. Okay, circle your answer, you're done. So it works like you'd probably expect. You multiply your numbers, your coefficients, and since you're multiplying with powers, you're adding those numbers. You're adding those powers to put the variable together. You don't have another x, you don't add anything to it, you just write it. Okay, good. Let's look at another example, and this will also be from your text. I like to use the ones from the text so that people reading the textbook can go back and make sure they read through the problem correctly and understood the steps and all that. This one's a longer one, but they kind of give it to us right away because they're saying, hey, this isn't so bad. You just do order of operations, and now you have x's in there. Who cares? I mean, with order of operations, you're doing parentheses, so you jump into those brackets first thing. Then you'd say, oh, I got more parentheses. You jump all the way inside to the 4x plus 1. You always go to the inside and work your way out, right? So on the inside, the 4x plus 1, can I put those together? No, they're not like terms. So I try to break down those parentheses some other way. What would I do here? Distribute. That negative x times both these pieces. So that's actually a negative 1x if I wanted to see it like that, right? Negative 1 times 4 gives me 4. X times x gives me x to what power? 1 plus 1 is 2. Okay. And then negative 1 times positive 1 gives me negative 1. Keep that x on there. And let's see what the rest of the problem is. I'll write that down. Because this piece came from right there. Okay, now we're inside those brackets, also known as being like parentheses, right? They're just grouping symbols. Can we put any like terms together? And hopefully you're going to say yes. What can we put together, Taylor? Or whoever said yes. Misha? Okay, so 2 plus 2 is, okay, so like terms, we're going to combine these. So we have 4. It doesn't matter where you write the thing. I'm just going to write it there. Minus 4x squared minus 1x. I'll keep my brackets. I could write them as parentheses if it made me more comfortable, but it doesn't matter. I'll keep writing it the same way. These are 2s. I guess I need to be more consistent with how I write that too. Okay. So now we can't condense it anymore. What do we do again? Distribute. Share that 3x with everything. It's like a distribution party. We're just going to do that every single time. Okay, negative 3 times 4 gives me negative 12. I didn't have an x except outside, so we'll just write the x. Negative 3 times negative 4 gives me, wait, a negative times a negative, positive 12, and I add my x powers to get an x to the third, okay. Negative 3 times negative 1 gives me positive 3, and then the 2 x's give me x to the squared. Very good. Okay, and then we still have this out front. I always have to ask myself, can I combine any like terms? Can I? 3 plus 2 gives me okay. And really, I mean, we don't have to do this, but just to make ourselves happy in the author, we can write this thing in order, right? Again, it would have been okay if you stopped with the original, but just to be safe, we'll write it the way the author would want it. Let's make sure you wouldn't get mixed up if it were written backwards. This is basically all we're learning tonight. But I'm going to give you lots of examples so that you can see it different ways, because there's different combinations I can do. If you get this part, though, you should get the rest of it. Okay, here's another example. Let's see if when I write it backwards, you're able to still handle it. Because we know multiplication can be written in any order, right? Still just means multiply. So when I write that, it's similar to the previous ones. That's a b, by the way, not a 6. It's 2b squared minus 7b minus 8 minus 5b. Look at the previous ones for a sec. We were starting with one piece on the left and taking it through, right? I think we can still do that even though it's written backwards. Sure. I mean, all you're doing is when you multiply polynomials, the idea is you're multiplying every piece times the other one. You know what I mean? Like you're taking that one and you're sharing it with everyone on the inside. So the negative 5b has to go times the 8 times the negative 7b times the 2b squared. You're hitting the pieces of the polynomial on the right to the insides of the other polynomial. So they've all came in contact and multiplied. So I'm going to distribute. Sure, you can write it backwards. Who cares? Negative 5 times 2 gives me what? B to the what power? 3, okay. Then I have negative 5b times negative 7b. So that's going to give me a positive 35b squared, because you're adding those powers again. Perfect. Remembering, of course, that there's always a power of 1 if you don't see it. If I had a power of 0, that wouldn't be so hot, would it? It'd be bad, because anything to the power of 0 is equal to what? 1. Okay, just making sure. That's why we know for a fact it's a 1 up there, not a 0, because a 0 means something totally different. Okay, now we have negative 5b times negative 8. What do we have? Positive 40b. You got it. Good. Look, and it's already in order too. How convenient. Let's see if we can mix it up some. I mean, it's going to do the same thing. Don't get too excited here, but we'll do our best to find an interesting one. How about something like this? I mean, so far this one on the right, like the negative 5b, that's called a monomial, only has 1 piece. I guess we could have, a couple pieces times a couple pieces, right? Sure, let's do it. Let's make our lives more interesting. Multiply. I got this from your textbook. It's actually number 32 in the homework, just so you know. But the idea, just like I said a second ago, is that you're multiplying the pieces of one to all the pieces of the other one, right? So, for example, that y is going to go times this y and times this 3, right? Then what? The 8 will go times the y, and then times what? The 3. Good. So you're just multiplying all the pieces together. There's a saying that people use for this. Whenever you have 2 things times 2 things, binomials being multiplied together. And you may have heard it before. It's called FOIL. Have you heard of FOIL before? Let me write it, because if you've learned it, you might like to be reminded this is what's actually happening here. You don't have, if you didn't already know it, you don't have to learn it. My little arrows show you what FOIL does. FOIL reminds people that when you're multiplying 2 times 2, or something with 2 terms times something with 2 terms, you do the first 2, the outside 2, the inner 2, and you're also going to take care of the last 2. So it helps remind people that they didn't forget any pieces. It doesn't actually mean anything more special than that. In fact, the arrows I just drew do the exact same thing. See, watch. First, that's y times 3, right? Wait, sorry. I guess I'll go in the order of the FOIL. First is going to be y times y, the first of each. Y times y gives me, okay, outer. That's going to be a 3 times a y, right? Plus 3y. Inner, that's an 8 times a y. That gives me 8y. Last, so the last 2 in each set of parentheses, and 8 times a 3 gives me 24. Okay. And I have like terms, right? 8 times 3 gives me, 8 plus 3, sorry, we can do the addition here. 11y. Look at that. Was that hard? No. Even if you didn't do it in the special FOIL order, even if you'd done, let's see, y times y squared, y times 3. Oh, I guess it does come out the exact same, doesn't it? 8 times y, 8 times 3. Okay, even without FOIL, you're just taking the pieces of one and multiplying it to all the pieces of the other. We don't really care how or why you do it. Just make sure it gets done. FOIL is something you may have learned in the past to help remind you to not leave any pieces out. That brings me to a thought, though. Probably you guys are okay with this, right? But what if you had more pieces? You couldn't call it a FOIL anymore. FOIL only works when you have 2 binomials. Like 2 pieces in one set, 2 pieces in the other. But the same idea would hold